I want to do an extended example of the way we use Taylor's theorem with remainders. So a typical example is we have some function like ln of x, and we're trying to estimate the value of ln of x at some number like 5/4 that would be inconvenient to calculate by hand. Let's start with just p1 of x, which is just the linearization that we're familiar with, but we'll call it p1 because we're doing it in the context of these Taylor series. We need to find a suitable point to center our Taylor series at. Often 0 is a convenient place, but log of 0 is not a convenient value. 5/4 is near 1, and 1 is a convenient value for the natural log, because natural log of 1 is 0. So we'll take a equals 1. We'll center our Taylor polynomial on a equals 1. And to calculate p1 of x, we need f of a and f prime of a. F prime of a is 1 over x, so then we take f of 1 is 0, f prime of 1 is 1, and p1 of x is 0 plus 1 times x minus 1. That's f of a plus f prime of a times x minus a. And notice we do get a line here. Now we can use this to approximate the natural log of 5/4. F of 5/4 is approximately p1 of 5/4. That's the whole point of a linearization. And we can plug 5/4 in for x in our function p1 of x. So p1 of 5/4 is 1/4. So natural log of 5/4 is approximately equal to 1/4. So far, we haven't really done any of the new Taylor polynomial stuff. This is all stuff we could have done with a linearization. Before we go on, let's draw a quick picture. Here's a sketch of log x. It's zoomed in to talk about the range we're interested in. So we're interested in the interval from 1 to 5/4, so that's pretty zoomed in. I'm exaggerating the curve a little to make it visible. And then we can draw this line, x minus 1. The point we're actually interested in is this point I filled in black, the point 5/4, whatever log of 5/4 is, and our estimate is this point above it, 5/4, 1/4. What Taylor's theorem with remainder lets us do is zoom in on this error, this thing we sometimes call R1, the gap between f of x and p1 of x. So what Taylor's theorem with remainder says in this situation is it says there is some c between 1 and 5/4, between x and a, so that f of x minus p1 of x, the difference between the correct value and our estimate p1 of x, is this formula, f of n plus 1 of c divided by n plus 1 factorial times x minus a to the n plus 1. N is 1 here, a is 1, x is 5/4. The second derivative of our original function, the second derivative of log x, is the derivative of 1 over x, which is negative 1 over x squared. So when we plug that all in, we get negative 1 over 32c squared. There is some c between 1 and 5/4, so that the error is negative 1 over 32c squared. Notice that there are no stray numbers or intervals or anything floating around here. Everything is written in sentences, sometimes with English, sometimes mathematical sentences like n equals 1. But I'm not writing 5/4 somewhere without comment. And I encourage you to do the same in your own work. Don't just write numbers and hope you'll remember what they mean later. If you're writing something down, write what you're doing with it. Either write it as part of an equality that tells you what it means and how it relates to other things, or write a sentence like there is some c between 1 and 5/4, so you know what this value is doing for you. Notice that we don't know what the c is, and we don't exactly care. We're not going to try to solve for c. We're not interested in the exact value of c. We have unknowns on both sides of this equation. Our error, f of x minus p1 of x, is an unknown, and our c, our negative 1 over 32c squared, is an unknown. And Taylor's theorem with remainder just leaves us knowing these two unknown things are equal to each other. The way we're going to use this is to estimate that error. We don't care about c, we care about the error. C is just a tool to try to find out about the error. So let's use this to give upper and lower bounds on the error. P1 of 5 over 4 is our estimate for natural log of 5 over 4, and now we want to know how good an estimate is it. So let's copy over what we said on the previous page. We know there is a c between 1 and 5 fourths, so that the difference, log of 5 fourths minus P1 of 5 fourths, is negative 1 over 32c squared. And to find an upper bound, we need to ask, what is the largest that negative 1 over 32c squared should be? In general, this is a single variable optimization problem. In Calc 1, you learn some techniques about how to optimize functions on an interval. But in this case, you might just look at this and know that this is an increasing function. As c gets bigger, this thing is increasing, right? Negative 1 over 32c squared, it's negative, and it's approaching 0 from below. So as c gets bigger, we get a bigger value, a value closer to 0 from below. So the biggest this can be is when c is 5 fourths. When c is 5 fourths, 1 over negative 32c squared is negative 1 over 50. And the smallest that negative 1 over 32c squared can be is when c is 1, when it is negative 1 over 32. And this is almost always how we will use Taylor's theorem with remainder. We're not interested in the exact value of c. What we're interested in is getting bounds on this error term, knowing the bounds on c. We're almost always interested in looking at this function. In our case, it's negative 1 over 32c squared, and just getting the quickest, easiest bounds that we can get on it. All right, so log of 5 over 4 log of 5 fourths minus P1 of 5 fourths is equal to negative 1 over 32c squared for some value of c. That just means it's between negative 1/32 and negative 1/50. The error has to be in that interval. By the way, that immediately tells us 1/4 must be an overestimate. Right? 0 is not in this interval. There's no way we're exactly right. In fact, 1/4 must be too big. That's not a surprise. That's what our picture showed us too. That not only did we have an estimate, it was something we knew was an overestimate. Now is a good time to pull out a calculator and check that we haven't made a mistake. So we can pull out a calculator and we can plug these values in. Log of 5/4 minus 1/4, it's about 0.2231 minus 0.25. The calculator says that's about negative 0.0268, which is indeed between negative 1/32 and negative 1/50. It's about negative 1 over 37.2. Let's use that to answer a related question. What are upper and lower bounds on log of 5/4? We can actually get that from the previous statement just using algebra. So we said log of 5/4 minus 1/4. The error is between negative 1 over 32 and negative 1 over 50. And then we can just add 1/4 to everything. So log of 5/4 is between 1/4 minus 1 over 32 and 1/4 minus 1 over 50. And then we can combine fractions to solve those. Log of 5/4 is between 7 over 32 and 23 over 100. And again, you can plug log of 5/4 into a calculator and check that it really is between these two values. Let's turn that up one step and now do it with P2. so using the quadratic approximation. But other than the fact that we're using the second Taylor polynomial, nothing is really going to change. First, let's estimate log of 5/4 using P2 of x. So again, a is 1. We know f of 1 is 0 and f prime of 1 is 1. F double prime was negative 1 over x squared. So f double prime of 1 is negative 1. So P2 of x is 0 plus 1 times x minus 1 plus negative 1 over 2 factorial times x minus 1 squared. And when we plug in 5/4 and we work that all out, we get exactly 7/32, which actually happened to be exactly the lower bound from our previous estimate, which won't always happen, but is sort of a coincidence in this case. And we can add this quadratic curve to our picture. This is a pretty terrible picture. I encourage you to draw pretty terrible pictures by hand because even bad pictures are often useful for just helping us visualize what all these values are doing for us. This is a quadratic. You can't tell just from this drawing that it looks like a parabola, but it's sort of like a parabola. The maximum is over to the right. This is a downward facing parabola, and we're only seeing the left half of this parabola. And I'm making it go through that lower bound on our estimate before, that 0.730 that we found. And again, we can try to get a better estimate by looking at the error, by asking what is the gap between the true value and P2 of x. So what does Taylor's theorem with remainder say? It says there's a c, it's between 1 and 5/4, and the error, log of 5/4 minus P2 of 5/4, is equal to the third derivative of f evaluated at c, divided by 3 factorial times 5/4 minus 1 cubed. The third derivative is 2 over x cubed. Right? It's the derivative of negative 1 over x squared. So you multiply by negative 2, and you get a 2 over x cubed. And when you simplify that all out, you get 2 over 3 factorial c cubed times 1/4 cubed. 3 factorial is 3 times 2 times 1. The 2 on the top cancels the 2 on the bottom. We end up with 1 over 192 times c cubed when we multiply everything out. And again, usually what we want to do with this, we don't care about c. What we care about are lower and upper bounds on the error. So again, to restate what we said on the previous page, there is a c between 1 and 5/4, so that log of 5/4 minus P2 of 5/4 is 1 over 192 c cubed. And we want to know what is the biggest and the smallest that 1 over 192 c cubed can be when c is between 1 and 5/4. And we know that 1 over 192 c cubed is a decreasing function. Right? As c gets bigger, 1 over c cubed is getting smaller. So the biggest we're going to get is when c is 1 on the left-hand side of this interval. So the biggest the error can be is 1 over 192. And the smallest the error can be is when c is on the right-hand side of this interval, when c is 5/4. And when we do that out, we get that that's 1 over 375. So what we know is that the error is between 1 over 375 and 1 over 192. These are small numbers, right? 1 over 192 is kind of a small number. So we actually know we're pretty close. We also know both of these numbers are positive. We know that our error is positive, which means we have an underestimate, which again is what my kind of terrible picture suggested. And again, we can just check this by plugging in. Log of 5/4 minus 732. According to a calculator, that's about 0.00439. If we plug in 1 over 375 and 1 over 192, they're about 0.002 and 0.05. And indeed, our error is somewhere in that interval. In general, Pictures are nice. Even terrible pictures, like these ones I'm drawing by hand, are good enough for a lot of purposes. And if you're not clear, there's all these numbers, what's A, what's X, what's R1, draw a picture and mark them on the picture. But once in a while, it's nice to look at a good picture. So here's what we were doing on a nice picture from Desmos. So this black line, the black curve, is log of x. I've zoomed in a lot. The x-axis only goes from 1.16 to 1.31 here, so we've zoomed in a lot to make this visible. You can barely tell that log x is curving. That black dot is the point we're trying to estimate. This blue line is P1 of x. The blue thing is actually a line. The blue dot is 5/4, 1/4. It was our estimate for log, our first estimate for log of 5/4. And this blue interval here is the interval we got by looking at the error estimate. We got that log of 5/4 had to be between 7/32 and 23/100 or whatever, and that's this blue interval. And then we drew this green parabola, and this is P2, and this green dot was our second estimate. And this green interval is the much smaller interval coming from the error bound on R2. So that error bound we just got on R2 tells us log of 5/4 has to be somewhere in this green interval. And the picture shows us that indeed the black dot is in the middle of that green interval.